Okay. Hi everyone. This is Mr. May. So in this lesson, I want to talk about how do we use a uniform magnetic field and a uniform electric field to be to make a velocity selector for charged particles. So um so what is a velocity selector, right? A velocity selector is a tool that allows charged particle with a specific velocity to pass through without diffraction when enter perpendicularly to both electric field and magnetic field. So let me show you what is a velocity selector. Let's say this one is the velocity selector. And then let's say you have a bin of charged particles that is moving in this direction with a speed of v. And then let's say all of these charged particle having a charge of q, right? And then moving with a speed v. Um, you know that not all of them will have a speed of v. Some of them may have speed of v2, v3, and so on. Those might be speed that is slightly less than or larger than the specific speed that we want. So for those particles that with other speeds, either that's higher or lower than the velocity v, will be when entered through this velocity selector, they will deflect to the left or deflect to the right. So for those particles that have different velocities, will not be able to pass through the selector smoothly or directly out of the selector. The thing is like how do we using the magnetic field and the uniform electric field to make this velocity selector. We know that. Let's focus on the on what happened in this selector. So let's say if you have a particle that's in this position, right? And then the reason that the particle will be deflect to the right side, let's say to the right side, that means that there must be some force that will pull the particle to the right, right? And for the reason that the particle will not be deflected to the left, because the force on the right side is obviously larger than the force on the left side. And also, like if the particle is pulling to the left, that means the left force is larger than the right side force, right? So the thing is that how do we orientate the direction of the electric field and the magnetic field to achieving two forces? Like the one of the force is to the left and one of the force is to the right side. So how do we do that? Some of you might already figure if we have a electric field that's going to the right side, then that means this particle will be experience a electric field to the right side, right? And this electric field is equal to Q times the E electric field. So the next question is that how do we orientate the direction of the uniform magnetic field so that the magnetic force will be pulling to the left side? Yeah. So how do we do this? In this case, we know that we can use in the right hand rule. This is your right hand. So you are using the right hand rule. And then let's say this is your palm. This is your palm. And then this is your finger, your thumb. The direction of your thumb, like pulling 90-degree with your right, this is 90-degree with your fingers. And then so this thumb is pulling this direction. That is the direction of the force. So we want to figure out the direction of the magnetic field, right? Okay, so when you go back to this equation, the magnetic force equation, you see that the velocity comes first. So your fingers, your other fingers, will be pointing to the direction of the of the velocity, because the velocity comes first in the cross multiply. So the direction of your palm, that is the direction of the magnetic field. Yeah. So in this case, if you want a magnetic field that's pulling to the left, you must have a magnetic field that is put in the direction of page. So let's draw something here. So you need to have a magnetic field that is off page, right? Okay, so right now you have two forces, magnetic force and the electric force. Okay, so now you should know that for the charged particle to be moved out of the selector without deflection, it must be that the net force equal to 0. The net force in this case is the electromagnetic force. So let's just combine that. So the net force must be equal to 0, right? And this net force is the same as the electromagnetic force, which is the electric force plus the magnetic force, which is Q E. Let me do this. QE plus QV B. Okay, and then you simplify that, you should get right, because you do the distributive property, you should know that, right? But one of the possibility is that if Q is equal to 0, right, that means the charge is neutral, no charge at all, right? Then definitely if you send a neutral charge particle moving through the selector, it doesn't matter like how large is your electric field or how large is your uh, electric field, magnetic field, they will not affect, they will not putting a force on a neutral charge, right? So that's not the case that we will consider about in this situation. The another case is that this term must be equal to 0, right? Because you want the net force to be equal to 0, then the the charged particles will be able to move out of the selector without deflection, right? So the electric field plus the cross product of velocity and the magnetic field must be equal to 0. How do we turn this thing to be in terms of quantities? Let's say in quantities V, E, and B. We don't want the vectors. We don't want like these vectors. We want them to be in quantities. So how do we do that? Let's draw a Cartesian graph. You know that, let's say we label the graph. Let's label this direction as the positive x direction and this direction as the positive z direction, and this is the positive y direction, right? Okay, right now when you watch back in this graph, right, and then you see that the direction of the electric field is pulling to the right side, which is in the direction of the positive x direction. That means the E can be just write down as E. So E plus, okay, for now the when you focus on the direction of the velocity, which is in the negative z direction. If this velocity have a quantity of v, and if this v is positive, let's say this one is positive, that means when you go back to this graph here, if the particle is moving in the negative z direction with a quantity of v, so to make this velocity as a negative value, you need to put a so negative v, right? And then you know that the direction of the magnetic field is all of page, which is in the positive y direction. That means we can just write down b, right? And also you know that the cross multiply of v and b, you need to times the sine theta here, right? The direction of the velocity and the magnetic field is 90°, right? So you can just put 90° here, so which is equal to 1, right? So after you simplify everything, you should get E is equal to VB. So you can just get V is equal to E over B. Okay, so for a specific electric field and a specific magnetic field, you can decide what charged particles will be able to pass through the selector without diffraction. So based on this, you know that the particles with velocity of E over B will be able to pass through the selector without diffraction at all, right? So in this case, if the velocity is equal to E over B, then there's no diffraction. But what about if the velocity is greater than E over B? That means the electric field must be larger, right? So when you look back to this free body diagram, you know that if the electric field is larger, that means you will have a larger electric force. So definitely the particle will be diffract to the right. Right? So what about if the velocity is less than E over B? So again, when you go back to the free body diagram, it will diffract to the left because the magnetic force is larger, right? Yeah. So that's everything you know. Let me summarize everything. So let me explain what is a velocity selector again to you guys. So a velocity selector is a tool that allows charged particles to pass through the selector without any diffraction when the net force is zero. So to make the particle to diffract to the left or right or no diffraction, that it depends on the velocity of the charged particles, right? If the charged particle is equal to E over B, then no diffraction. If the charged particle's velocity is greater than E over B, then it will be diffract to the right. If the velocity is less than E over B, and then it will diffract to the left. Yeah, thank you for watching and listening. Thank you.